So, good afternoon. Welcome to this next class for ETS, Education and Teaching Studies. And I am sharing a PowerPoint with you this afternoon as we continue our discussion on the science of learning, which is the theories that have been amalgamated into our current understanding as researchers and as educators, what we currently understand in this general field of the science of learning, which is a bringing together of the neuroscience, bringing together of psychology and education as we understand and unpack where people are currently having an understanding of how we learn, of how the brain receives information, processes it, retrieves it, and the learning that takes place. So we are continuing this theme by having a look at a specific aspect of the science of learning, and this relates directly to what is called the cognitive load theory. So last week we spoke about the information processing model, and we had an understanding of how information is in what the input is of information into the brain and how it gets processed, and then there is an output component. So this cognitive load theory is part of that model, but it's a specific area that looks at how much information the brain can process and store, and it has been described by a researcher called Dylan William as the single most important aspect of the science of learning that teachers need to be aware of. And it is grounded in very good research, and an understanding of how this works is useful for us as educators when we are instructing and thinking about our pedagogy and didactics and how we put our learning together in the classroom and what it is that we need to be aware of as we do didactics and understanding. So the science of learning is all based on our understanding of the human brain, how all the lobes in the brain have specific functionality, and the understanding that all the parts of the brain work together in this symphony of figuring out the stimuli that we receive from the world around us, how we process that, and what is going to be stored in our long-term memory, and what we're going to use for output. So our understanding is that the human brain can only process relatively small amounts of new information that it receives simultaneously. However, we know that large amounts of information can be stored once they have been processed. They can be stored for a lifetime that the person's brain is functional. So this cognitive load theory has got to do with what is happening in working or short-term memory. And in working and short-term memory, we had a look at that as part of the information processing model. So the average person can only hold approximately a relatively small amount of chunks of information in their working memory at any particular time. And long-term memory is holding information for a very long time once we have encoded that information into the brain. In our long-term memory, we are storing information in what is referred to as schemas. So these are constructs or little boxes of storage places, and these schema are our way of making sense of the world. They're often related to language and our understanding of the words that we give to everything that's happening in the world around us. So the understanding of schemas comes from Jean Piaget. The work of Piaget was the foundational work that he said we are building up our concepts, our constructs, our understanding of all the parts of the world around us as we are growing and interacting with people and things. So when we have a look at this amazing brain, it's all these parts of the nervous system that are working together and that are creating this store of different kinds of memory. And remember, we spoke about memory, long-term memory, as having different kinds. We've got memory related to things that have happened to us, episodic memory. We've got semantic memory and understanding of the world and anything that we have studied, the meanings behind things. And we have got procedural memory that relates to how things get done, the processes, the steps of doing something like driving a car or doing some kind of activity, playing a musical instrument or so. So the long-term memory, once information has been encoded into long-term memory, it stays there for a relatively long period of time. Okay, so cognitive load theory has its roots in the 1950s, where it was where people were studying and having a look at how our short-term memory functions. And one of the key studies was done by Miller, and he started this idea initially that we can only process a certain amount of information at a particular time. And in his studies, the magical number of 7 was the number that people could remember. So, for instance, if you give somebody a set of numbers or a set of words to remember, and you like a telephone number, then and you start off with very short numbers, give them 2 digits, people will remember that easily. Give people 3 digits, they'll remember that easily. 4 digits, 10, most people can remember that. 5 digits, most people can remember. 6 digits, now some people can't remember that. 6 digits in a row. 7 digits is kind of the average. And 8 digits in a row. A lot of people won't be able to remember, but there are some people who can. and then 9 digits. Even fewer people can remember that, but by the time you're getting to remembering 7 items consecutively, 10 items consecutively in a row, that's when people's capacity for short-term memory starts to break down, and then you can't remember that telephone number well and sequentially. So this, in the 1950s, then these crucial bottlenecks of understanding that the short-term memory can only take a certain amount of information at a time to process. And the number of 7 in various different experiments has been shown to be quite consistent across populations. So 7 items plus or minus 2. So some people can remember up the 5, they're on the lower end, and then other people can remember 9, up to 9 digits consecutively. And so that's where we get the 7 plus or minus 2. So a range, 5, 6, 7, 8, 9 digits or items, things that you need to remember, a list of words or so. And after that, the short-term memory, to get the cognitive processes are bogged down. So that's why this cognitive load theory has a long grounding. It's got a long tradition of where it comes from. And then building on those experiments, we spoke about Atkinson and Shiffrin. They did a lot of work in the 1960s, and their information processing theory has become the basis of a lot of the way that we understand the input of stimuli from the world around us, sensory input, the various different memories that we have, sensory memory, memory of how we remember the visual things that we see, memory of the auditory things that we hear, and then this working memory is the memory of that we're talking about, the short-term or working memory, the items that you can remember for a short period of time in order to do something with them, like digits that you need to add up or do some calculations with, or you hear some words that somebody said in a lecture, and then you need to write them down before you lose them or forget them. So the Atkinson and Shiffrin model, we discussed in a bit more detail how the input processing and output work as a within the brain. And then building on that information processing model, Chase and Simon's work in the 1970s worked on this idea that we need to chunk information. And I'm sure that you've all heard of chunking, where we break down lots and long, complicated presentations of lists or digits or whatever needs to be remembered. We break the information down into smaller parts, and so we chunk it, and we develop schema. Schema are the words that we give to the things that we understand in the world around us, and this helps us to organize information, to put it into some kind of way that we can then make sense of it and remember it in order to be able to retrieve that information later. And then we go on to the 1980s, and here we have this idea now being given the actual terminology of cognitive load theory by researcher Sweller, and this is a in-depth or expanded view of the cognitive information processing theory or model that was developed previously in the 1960s. So this theory has a long tradition, and it's got a long a long chain of evidence that has been presented over numerous, that has been studied since the 1950s or so. But the actual naming of cognitive load theory was by John Sweller in the 1980s, and he was an educational psychologist who said that we need to focus as educators, as teachers, as people who are understanding how human beings learn. We need to have much more focus on the idea that we cannot present huge amounts of information and expect that to be remembered and learned and acted upon. So as educators, we need to be cognizant of the amount of information that we present to children as they are learning this. Okay, so we're going to go on, and cognitive load theory has been considered as one of the most important theories for us as educators to understand and to have a good idea of how this can be translated into the classroom. And this theory has been supported by numerous research, randomized, controlled trials where people have been given information that they need to, that they hear, and then they need to, repeat that, like digits, numbers, words, lists of facts, and so people can only remember and give you back a certain amount of that, and that magical number of 7 plus or minus 2 has remained quite consistent across most of the research that has been done. So when we are teaching children the new content and new skills, it is most effective when we are providing the content in smaller chunks, when we are breaking it down from the simple steps to the more complex ones in a clear manner. Okay, so let's go on. And just have a look. So cognitive load theory has got 3 types. Oh, 3 types of load that we think about, and they have been given these terms: intrinsic, extraneous, and germane loads. And these are crucial for us to understand as teachers. So I'm going to go and explain a little bit about what each one of these mean. So we're going to start with intrinsic load. And intrinsic load is the amount of mental work associated with a learning objective. So you want somebody to learn a particular item of work, and this is how much mental effort is associated with this. So this depends on the complexity of the information that you are presenting. So let's say that you are trying to present something about a complicated scientific experiment or a complicated maths operation. You need to explain a concept, something, in physics or science that is a really difficult thing to understand. The information is therefore complex, and so the more complex the information or the topic is that you need to learn, the higher the intrinsic load is that that you need, that information carries. So you need to have much more psychological energy and attention in order to be able to understand that information. And it might take you longer, and you might need to have many more little steps and lots of things to build on the underlying understanding so that you can understand a complicated thing like maybe string theory or scientific concepts that are really complex. So the underlying mental load, that's a mental work that is associated with a complex task, means that the intrinsic load is higher. And some things the intrinsic load is lower, so it's a relatively easy thing to understand. It's something that you come across every day, so it's easier for you to figure that out. So that is the intrinsic load. And the extraneous load is everything that is associated with distractions around the thing. So when we're speaking about extraneous, it might be that for instance, the way the information is presented is in a worksheet that's got lots of distracting pictures or lots of other information around it that is distracting from the key core concepts in the intrinsic load. And then when we speak about germane load, this is the relevant load in the mental work imposed by the instructional activities that will benefit the learning that needs to take place. So when we are looking at germane load, this is what is it that the person actually needs to do with this information that they have learned, what goal is achieved, where are they taking this information, what must they be able to do with it, must they be able to do a calculation or make a poster, or what output is required. So one then is taking the intrinsic inherent value of and complexity of the task and figuring out what you need to do with it, and trying to in germane load. And then extraneous is you have to then also be able to filter out things that are distracting from the message, something in the background of a slide, or something irrelevant that is distracting and reducing the mental capacity that you are able to focus on and attend to with the particular task at hand. So we want to reduce extraneous load, and we want to focus on the content and what must be done with the content, what is relevant load that is that the instructional activity actually requires the person to do. So we are, as teachers, we're trying to constantly reduce any irrelevant extraneous load. We are trying to we're being very focused by increasing and ensuring that the germane things that we want people to learn are clearly stipulated in textbooks or worksheets or PowerPoint presentations, so that it's very clear what the person must learn. And we are managing the complexity of the intrinsic load by breaking things down, chunking things, breaking them down into smaller steps, ensuring that they're presented in a clear format from the most simple to the most complex, and giving examples of how to do a particular task. So we are very clear that we are able to break these things down and really understand them. Okay, so let me go through these different types of load again so that we have a clear understanding. So cognitive load theory is this theory that our working memory is limited, and because it's limited, we understand that there are different things that are impacting on the processing of information. Our goal is to reduce irrelevant load, to increase the relevant load, and to manage the intrinsic complexity of the task. Okay, so I'm just going to move on to this a little bit more. So here is another way to think about these different kinds of cognitive loads that information places on the brain. Intrinsic load, a measure of how many novel things a learner has to do at once to complete a particular task. So this is the definitions of these types of cognitive load. And so here you can see that this intrinsic load has got to do with the new things that need to be learned, the novelty of it and how complex it is. If you think about being able to do a particular maths calculation in a new different algebraic equation, then there is intrinsic load associated with that. The extraneous load, extra's got to do with extra things that are peripheral, that are distracting. This is a measure of the load imposed by the task, which does not support the learning. So this is things that are not supporting the learning, and we need to be able to filter those things out and not be distracted by that particular load. And then if we have a look at germane load, this is a measure of the extra load imposed by the teaching activity to support the learning. So the actual didactics that are being done, what you're doing in the classroom, the actual method that you might use to teach the science experiment, or the method to teach the particular whatever equation that you want to teach. So the actual activities might assist or they might not assist the learning process. Okay, so if the information is complex and novel and new, we need to be more careful as educators that we are reducing the irrelevant things in the worksheets or the textbook or the classroom or the posters or the presentations that we're presenting. And then we need to be careful that we are not making extra load to understand these things, because we might have pictures that are maybe not relevant to the content, or we might have some kind of experiment that maybe doesn't relate to what you're trying to show, science experiments, or posters, videos that we're showing. So we want the domain load, how the information is presented, to be as simple and as easy to understand as possible if the intrinsic task is complicated that the person needs to understand. And all of this is because we want information to be processed into long-term memory, and long-term memory, in order to process information, it has to go through short-term memory, to be rehearsed, to be drilled, in order to go into the long-term memory storage of the brain. So we are trying to we're trying to be very, as teachers, we're trying to be cognizant of the complexity of the task and how we present the information to learners. Okay, let me go on to the next slide. So this is just the goals that we are trying to do. We are managing the intrinsic load, and this is the complexity of the material. So if the material is very complex, we are making it simpler, we're reducing the steps. If the material is simpler, then we were trying to reduce the extraneous load, and so we are reducing any distractions and unnecessary things that are distracting from the intrinsic value of the material that we're trying to teach. And we capitalize on the domain load. So this means that we are careful as to how we present it, what methodology we use, how we set up the laboratory, for instance, how we develop the worksheets, what the PowerPoint looks like, what videos we use. We capitalize to ensure that the domain load, the way the information is presented, is in line with the complexity of the content that is being taught. Okay. So the goal of all of this, of understanding how the short-term memory is the bottleneck for processing information, the goal is to ensure that we are developing complicated and accurate and the correct schema of that particular domain. So the schema would be the concepts, the constructs, the words, the terminology of a particular field of study. So if you are doing geography, let's say, you need to understand how what the world looks like. You need to understand how the oceans and the planets work, and the weather patterns, and the contours on the maps. So all of these are schema that you are building up an understanding of that particular field of study. We are doing this for all knowledge areas that you might be in. And generally for any field of study, the knowledge is hierarchically organized. So that means hierarchically is there's simple concepts, and the simple concepts build up together to make much more complex concepts, and how we start to understand the interactions between the different constructs or schema of that particular field of study, because we are trying to build complex networks of constructs of concepts in long-term memory. So the long-term storage capacity of the brain, people think is unlimited. They haven't been able to figure out, ways to figure out how much information the human brain can store. There are lots of estimates, and of very, very large figures. But the thing that is the bottleneck is this short-term information, where information has to go through short-term memory as it enters the brain, and into working memory as the information is retrieved from long-term memory into our consciousness, so that we are able to do something with that information. And so understanding that our role as teachers is that we are managing this process of the cognitive load that our learners are being exposed to all the time. So we are being careful as to how we are presenting information in relatively small chunks. We make sure that one bit of information builds on another. We present texts and words and explanations and graphs and posters and videos and real concrete material, all our teaching aids. Everything should be presented in a way that the information is that the presentation is relevant to the intrinsic load of the material, how complex or simple the material is, and that the information is we are reducing any extraneous cognitive load, things that are irrelevant, that are distracting from the presentation of that information. And we want children and people to develop accurate, complex understanding of the particular task or particular domain that we teach them, that you are teaching children to do. Okay, so there is a lot of spin-offs that have come from the understanding of cognitive load theory that have some relevance for us as teachers. And I'm briefly going to go through some of these strategies that we recognize have developed because of the this understanding of cognitive load being a bottleneck of information that gets processed in the human brain. Okay, so I'm going to start with the first strategy. So these are things that you can bear in mind when you are developing your worksheets, when you're putting together lesson plans, when you're thinking about, as an educator, how to present information to learners. And we're going to start with number 1, and this is called the worked example effect. The worked example effect is a strategy that is very widely used, and it has been well researched to say that it is effective in teaching whatever content. And this is where a person will give the new learners some example that you work through let's say a maths calculation or a science experiment. You are working through an example to show them the steps and exactly how this particular thing works. So the example is and if you do many examples, then you start to understand the underlying principles behind that particular aspect that is that you want to teach. Then we have another strategy, number 2, called the completion effect. And this is where you then give part of the example, part of the text, or part of the drawing, part of the calculation, let's say, and you ask the child to complete the missing steps or the missing parts, the missing words that are that have been left out. So you are you're giving some of the information, and the person needs to complete the whatever it is. And so this is a very useful strategy for allowing people to figure out what the underlying principles are that are being taught. So we're going to move on to number 3, which is the split attention effect. And in this thing, you will take a page or a worksheet or a PowerPoint slide, and you divide it into 2 parts. So you can, for instance, have a left side and a right side of the page, or a top and a bottom of the page, and you are splitting the information into different kinds of information that's being presented. And this is very useful when you've got to, for instance, explain a graph, or some kind of a picture. So on one side, you'd put the picture, on the other side, you'd put some words. Or you would have a graph on one side, and on the other side, you'd have some keywords of what the words mean. So the split attention effect, you will often see that being used in PowerPoints, where there is some text associated with a picture or a graph or an image. And so that is also a useful strategy, that you are presenting information in 2 different ways, but it's explaining the same thing. Another strategy that relates to this theory of cognitive load is called the modality effect. And we use the modality effect when we are presenting information in different ways. So different modes of information. Can people just turn microphones off, please? So here you could present a visual image. You're presenting something that you can see. So it could be a video or a picture or a poster. There's a visual thing. And you could present the information as well in an auditory way. So you speaking it or listening to a podcast or listening to the video. So visual and auditory are the two main modes that we use to present information. But you could also allow people to do physical, tactile, touch something, draw it, or use clay, model something. Uh, Science is great for this because there's lots of equipment to use. So anything that is also concrete is another mode, a mode of information. So with the modality effect, we want to have um, uh, as many different modes of input as possible. So if we can do visual, auditory, and tactile, and sometimes you can even do taste and smell if you want to, have some aspect of whatever you're teaching, and you're able to have food associated with it. You can taste things. So the modality effect is crucial for ensuring that information is processed well and goes into long-term memory. Then we have the redundancy effect, and this occurs when we are able to remove any redundant information that is that will be directly impacting on the construction of the schema in long-term memory. And so this is where we are actively thinking about what can we remove, what can we take away that is not part of the intrinsic load. This is part of the extrinsic load, but you will also see people refer to redundancy effect, where where children might learn something associated with whatever you were teaching, but that it wasn't absolutely relevant to the task and to what was required from the particular content that they needed to learn. Okay, so we're moving on to strategy number 6, which is a strategy called the imagination effect. And this strategy is where you are asking children to use their imagination in order to picture something in their mind. And this imagination effect has been shown to be very useful for teaching complicated theories, complicated things. So you could say to a child who has some understanding, let's say, of the universe, or stars or planets, you could say, imagine the sun. Imagine the sun as a circle or a sphere, and imagine the planets going around the sun. And you can draw on people's understanding, current understanding of a particular topic, in order to ask them to think about in their mind, to imagine the content. So we can also do this in very concrete ways. And you can have people just think about the steps that they would use in order to do something, like basic things like cutting out a shape. What kind of shape would you need to fit into a particular puzzle piece. So all sorts of things where you're just asking people to think about it in their mind. And that process of imagining doing something or imagining something happening is useful because you are drawing, you're retrieving prior content out of long-term memory, you're retrieving it into short-term memory, imagining something with it, doing things with it. And the human brain is very good at fantasy and imagination. And then that can also be a technique that you can use to strengthen the learning of a particular content. So we're going to move on to another strategy which is useful for teachers, and this is the isolated interacting elements effect. And this is a good strategy to use when the content is particularly complicated. So if you want people to learn a very complicated theory, something that is has got lots of different parts to it. For instance, if you're doing a set work novel or a play in English, there's many chapters or many parts to the particular text. And so these parts are, you need to know a lot of the characters, let's say, in a play, and they come together as one novel or as one film, one video, but there are lots of different elements that are all interacting together in order to make synergy, in order to make a particular product. So what we would do as teachers is that we would then isolate some of the elements and draw them out, and you would teach them separately as parts, and only later start to make the connections and the relationships between them. So for instance, you could take the characters of a novel or a play, and you would look at one character at a time. Is this person the protagonist, or is this the heroine? Is this one of the side actors? Maybe it's the chorus in a play. And so you would be looking at the isolated things, and then you would interact and combine them later to make connections and interacting them. Number 8 is the expertise reversal effect. And this is where students are becoming more proficient at solving a problem or doing a particular item. And so you gradually give them more complex things to do as they become more and more expert at solving a problem or doing some strategy. So that the learner is becoming the expert, and you could even have children then teach each other, or teach, the expert children can teach other novice children a particular thing. So expertise reversal effect is a useful one to use as well. And then number 9 is a guidance fading effect. And this is where the teacher starts off by giving a lot of direct instruction and a lot of help, a lot of worked examples, a lot of guidance. The teacher is quite involved. And as the person becomes more proficient at the particular thing, let's say playing a musical instrument, the guidance of the the teacher would fade away as the person who's learning the task becomes more, as the person becomes more proficient. And then lastly is the goal-free effect, and this is the ultimate thing that you're trying to learn. You're trying to, let's say, find out what some set of statistical information might present to us. So you don't really know where it's going to take you. You might give a lot of different data, and you might be able to say, what can you infer from all of this graphs and data that's presented? Can you figure out something that is useful, that is meaningful for us to tell from whatever this is really this information that is here? So the goal-free effect is not often used in primary school or high school education, because we have very clear goals and outcomes that the curriculum wants us to achieve. And often the goal-free effect is what will be happening in research that people are doing at higher levels, in a PhD study, for instance, where you are trying to make sense of a lot of different information without really knowing sometimes where it's going to take you. So this is the cognitive load theory, and there's a lot of information on it on the internet. There's some readings that are in the unit, and there is a particular assignment that you need to do for this unit for this this week, and that has got to do with understanding those 3 different types of cognitive load: the intrinsic, the extrinsic, and the germane loads, so that you can apply this to your teaching and come up with practical examples and practical ways that you can put this into place in your own teaching, whatever subject you are teaching at school. Okay, so there are all the examples, the different strategies. And remember that as teachers, our job is to involve learners. And one of the quotes from Benjamin Franklin for teachers is that if you tell me, I forget. If you teach me, I might remember, but if you involve me in something, I will learn. And so we want to involve our children in as much physical, hands-on, real activities, then concepts get well learned. Okay, I'm going to go back to the chat and see if there are any queries or questions there. Please make sure that you are working on the next set of questions for the assignment 3. So you know the routine is that you need to do one little mini essay on the question topic for each week, and then those will be put in for the next assignment 3. Just to remind people that for this particular module, there are 5 assessment tasks across the year, and we have done assessment task 1 and assessment task 2. You are now working on the 3rd assessment task, and I will check that that the next set of things are open for you to work on in Moodle. Okay, So let's have a look in the chat if there are any questions and if there are any queries that that I can have a look for you here. Okay, someone says about the forgetting curve. Oh, I'll just check on Moodle, forgetting curve and cognitive load theory. It was one today, one next week, but we'll get to both of those. I'll make sure that they're both open for you, no problem. And we are, just to let you know, that we are going to be marking assignment 2 that's come in, and as soon as those marks have been moderated, we will let you know that they are open for that. Okay, so remember that you have tutors to assist you, and that your tutors are there to help you with any questions and queries that you need to do. Please do ensure that you are checking in with your tutors if you need any assistance in order to understand and to do the learning tasks that are required for this module.